transform length has to be twice of what it is? Let me think. Let's see. I'm going to just write a note here and then we have to account for a transform length which is double the input. So, okay. There are other tricks up our sleeve that we didn't even account for yet, like using Chinese remainder theorem and so on. Anyway, let's just assume this is correct and move to the modulus computation. So, one thing that has to be true is that our transform length, I wish I could just clear all this really fast. There probably is a faster way to clear this, but okay, so if we have a transform length of L, which is equal to 2 to the L, as I said before, then L must divide our modulus minus 1. This is fine. This is a really easy constraint to satisfy, mostly because most of our moduli, a typical modulus is going to be some factors f1, f2, ... f k times 2 to the power of, like, I don't know, some j plus 1. And more often than not, this j is greater than or equal to L. The only thing is, computationally, we just need to assert that this is the case right here. So if we go to our find suitable moduli, we just give it, well, yeah, we can just give it our transform length here. So for example, defun find modulus for n digits, we get the following. So digits, find suitable moduli with our transform length, which is going to be a multiple value find of our let's see, we have our base and then our log length, which is find appropriate base length. Keyword width. I won't do that yet. Actually, I will. For 64 bits. And then we find the suitable modulus for expt 2 to the power of our log length. And then we'll just do 1. So let's try this function. Find modulus for n digits. Let's do expt 10 to the 9. Okay, so that's a modulus that we can apparently use. Let's see, what else? I want to x equal first. factorize x. Oops, I meant factorize 1 minus x. So the factorization of 1 minus x is 2 to the power of 30 times 3 to the power of 1, which makes sense because, as we saw before, our for 64 bits and 10 to the 9, we have 2 to the 30 here, which let's write this out. So what this is saying is that our proposed modulus is equal to 2 to the 30 times 3 here, 3 times 2 to the 30 plus 1. Now we check if our transform length divides that. Well, our transform length is 2 to the 28, so 2 to the 28, which clearly divides 3 times 2 to the 30. I mean, it's just this exponent and this exponent cancel. So yeah, that found a suitable modulus for that number of digits. Let's look at something less egregious. Let's say we only want to calculate 1,000,000 digits, so 10 to the 6. We see that we can get away with a much larger base size, and we can get away with a transform length that's much smaller. 2 to the 18. Yep, our transform here is only 250,000 elements long. Let's see. All right. We can ignore the base here. So let's return values base and the modulus. So here is, if we do this function now, find base and modulus for decimal groups 10, let's exp 10 to the 9. With a word width there. Our base would be 262, 144, and our modulus is such. Am I returning these in the right order? Yeah, I think I made a mistake earlier. This is the... Oh, no, never mind. Wait. Let me make sure. The base and the log length are given in the right order, and these are given in the right order. Oh yeah, yes. Okay, so if I did 10 to the 6 here, yes, our base is this really large number. Our base is almost 1,000,000. Sorry, it's almost 10 million, and our modulus is pretty small. One thing I need to think about is whether that modulus is appropriate. Anyway, I'm gonna stop streaming for now. Some of these things I'll have to think about a little more. This actually doesn't feel like it's right. This is saying that we have a base which is really large, but a modulus which is much smaller, and I've been saying that the base and modulus must be, or the base must be less than or equal to the modulus. So this is a little curious. Maybe I need to do some sort of reverse search. Anyway, I will